Okay. Question 3. Question 3 states if f and g are vector functions of x, y, and z, such that their components have first-order partial derivatives, prove this statement. Okay, so how do we prove this statement? To prove this statement, what we need to do is work out the left-hand side of the equation. So LHS, okay? Work it out until it's into its simplest form. Then work out the right-hand side of the equation into its simplest form. Okay? If this statement is true, then you should see that in the simplest form, these two statements will be equal. Okay? Note that f and g are vector functions. Okay? Vector functions. This is not the same as vectors. Okay? For example, 2, 3, 5 is a vector, whereas x, y plus x, and z squared is a vector function, right? See? Vectors contains number in the entries. Vector functions contains functions in the entries. See, this is a function of x, this is a function of x and y, this is a function of z. Okay, so that's what vector functions are. Each entry is a function. Okay, so let's start with the left-hand side. The left-hand side, hold on. Okay, yeah. I just wanted to get my solutions. Okay, so the left-hand side states the divergence of f, g. Okay, so this is the LHS. So by the way, this curly sign under each letter means it's a vector. Okay, it's a curly sign that stands for this is a vector. Okay, so how do we do this? What we need to do is let f be the vector function a, b, c, and g be the vector function b, e, f. Okay, take note. A, B, C, D, E, F represents functions. They don't represent letters. Okay, they don't represent letters. These are all functions of x, y, z. Okay, so A is a function of x, y, z. B is a function of x, y, z. C is a function of x, y, z. D is a function of x, y, z. So on and so forth. Okay, so all of these are functions. Okay, meaning to say we can differentiate them. Okay, we can differentiate with them with respect to x, with respect to y, with respect to z. Okay, so take note of that. All these entries are functions, not numbers. Okay, it's very important because later on we need to take derivatives of this. And if you think these are numbers, then derivative of a number is 0. Okay, so now we need to take the div of this. Okay, so we haven't gone through what's the definition of div, right? Div is the short for divergence. 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 Okay. So what is the definition of divergence of f? Okay, divergence of f means nabla dot f. Okay, nabla dot f. So remember, nabla, the definition of nabla is a column vector whose entries are partial derivatives in each direction. So partial derivative in x, partial derivative in y, partial derivative in z. Okay, remember this is my notation. Partial derivative, I abbreviate it as this. Okay, so this is just a short form. Dot f. Okay, so suppose f is has the form of a, b, c. So divergence will eventually become, so this Okay, so this times this times this times this, and then you add them all together. Okay, I'm using times loosely because I'm not actually multiplying them. I'm taking the derivative in each entry. Okay, taking the derivative in each entry. If these two were numbers, I multiply them. But now we're taking the derivative operator and the function. We just act them upon each other. So plus this plus this. Okay, so this is how you get the divergence of a vector function. Now, what about curl? Curl of f means nabla cross f. Okay, so suppose, okay, so nabla is, the vector function containing partial derivatives. Then f, let's just say it's in the form a, b, c. So how do we take the cross product of a function? So remember, to take cross product of a function, you need to find the determinant of a certain structure, and that structure is ijk in the heading. Okay, then in the following row contains the first entry. Okay, the first column vector entries. So the x, y, the z, and then the next row will contain the second vector's entry. So a, b, c. Okay, so to do this, you need to take the Sarusus rule. So you copy the first two columns, copy these two, I, j, the two derivatives, two entries, and then you need to do the criss and cross. So this times together, this times together, this times together. Add those results up, minus this results, minus this results, minus this results, times together. Okay? So this is curl. So this divergence and curl, and I forgot to talk about gradient. Okay? So there's a certain vector operation called gradient of a function. So I misspoke. Okay, I said the wrong thing in the first time I introduced this. So this should be a scalar function. Okay, I'm going to change this then. I'm going to change this to phi. Okay, gradient of phi. So gradient means this, the nabla operator, scalar multiplied with phi. Okay, the nabla operator, scalar multiplied with phi. So this would be x, y, z. And what do? I just treat this like expansion, right? Expand into here, expand into here, expand into here. So this will be, this, this, this. Keep in mind that this is my abbreviation for that, okay? Partial derivatives. And also this for that, okay? So that's how you take the gradient. So in summary, we have three types of operation using nabla. Gradient, where you scalar multiply nabla with phi. Then divergence, where you dot product nabla with nabla with f, and then curl, where you cross multiply nabla with f. Okay, and it's also important to know that this is a scalar function, whereas these two are vector functions, right? Vector vector function and vector function. It's because dot product and cross product can only happen to vectors, whereas scalar multiplication here, okay, you scale and multiply. Okay, so this is a fine. Okay, just remember that this is a scalar function. Okay, just FYI, scalar functions, right? They're not the same as vector functions. So for example, a vector function would be something like xi plus y squared j plus z cubed k, something like that. Whereas, so this is a vector function. A scalar function would be something like x squared plus y squared. Okay, what's the difference between these two? See, the vector function has vector components. I, J, K. Whereas scalar functions don't have I, J, K. They're simply just a number. Okay, just a number. No I's, no J's, no K's. They don't have direction. See, vectors means they have a magnitude and direction. So the direction is indicated by I, J, K. Whereas scalar functions is what we already know before vectors. Okay, so yeah, we can finally start with this. So let us find this. So remember we need this. So we want to find the divergence of this, right? Let us first process the brackets. So what is f cross g? So let's find f cross g. To find f cross g, we need to find the determinant of this structure. I, J, K. So f entries are A, B, C. G entries are D, E, F. And then let's take Sarous's rule in order to find this determinant. Right. So copy the first two columns, I, J, A, B, D, E. Then after that, you do Chris's. Okay, so Chris, Chris, Chris. All these under the line must be multiplied together. So BFI plus CDK plus AEK. Now we need to subtract away the crosses. So cross, cross, cross. Okay, so multiply each of the lines together. So minus AFJ minus CEI minus DBK. Okay, if you group them together, so group the like terms together, the I with the I, the J with the J, the K with the K. Okay, factorize all the unit vectors. You will get BF minus CEI plus CD minus AFJ plus AE minus BDK. Okay? Okay, but this is only F cross G, right? What we really want is divergence of this result. So remember, divergence means we need to find nabla dot F cross G. Okay, so let us replace nabla and F cross G. So nabla is partial derivatives in each entry of a column vector. Then dot product with the result that we got. So see, just copy the result that we got here. This, right? I'm gonna write it in column vector format instead of IJK. So BF minus CE, CD minus AF, AE minus BD, and then close bracket. Okay. Okay, so how do you process the dot product? This act on this, plus this act on this, plus this act on this. Okay? So this will become, okay, I'm gonna write it out in full first. So this act on the first entry, plus this act on the second entry, plus this acting on the third entry. Okay. So how do we perform this differentiation? You see, this is a product of two functions. Okay, the product of two functions. So to differentiate this, we need to use the product rule. Okay, I'm just gonna put a reminder here that recall that the product rule states when you differentiate u and v, this becomes u v prime plus v u prime. Okay, prime means derivatives. So differentiation of u times v is u v prime plus v u prime. So that's what we're gonna do with b times f here. But we cannot use prime, we must use derivatives. So this and this. Okay, so bx means b differentiated with respect to x, and then fx means f differentiated with respect to x. Okay, so here I applied the product rule. Okay, so I'm going to apply the product rule the same here for CE. Okay. So if you apply the product rule for CE, it'll be minus CXE plus CEX. Okay, so product rule is differentiate, keep, differentiate. Okay, differentiate, keep, differentiate. Next, I'm going to do this derivative now. So again, product rule for C and D. So differentiate, keep, plus keep, differentiate. Okay, now I'm going to do minus AF. So minus differentiate. Oops, it's supposed to be wired now, right? So differentiate, keep, differentiate, plus now this one. So differentiate, keep, differentiate, minus this one now. Differentiate, keep, keep. Sorry. Differentiate, keep, then keep, differentiate. Okay, when I say keep, right, I mean keep it the same. Okay, when I say keep, I mean keep it the same. Okay, so now what we need to do, let's expand all the brackets. Okay, so these negative signs, I'm going to distribute it, all of them. Okay, all of them. So in the end, we will get you know what I'm gonna do? I'm gonna copy paste it because wow, this is so long. Yeah, sadly you cannot do this in exam. Okay, if you expand the brackets, this becomes minus minus. This becomes minus and minus. Okay, so this is already in simplest form. You cannot simplify it any further. So this is the result of the left-hand side. We'll keep this in view later because we need to compare it with the results on the right-hand side. Now let us move on to the right-hand side. So the right-hand side states G dot curl of F minus F dot curl of G. So let us find out the curls first. Curl of F, okay, by definition means nabla cross F. Okay, nabla is partial derivatives in each direction. F, we define it to be A, B, C, where A, B, C are functions, okay? Now, to find the determinant, what we need to do is, to find the cross product, we need to find the determinant of this structure. Okay, so to find the determinant of this structure, let's use the crisscross method. So copy the first two columns. Okay, now we need to do crisscross. So this, this, this. Okay, how do we interpret this? So usually if these are numbers, you multiply them together, right? If these are numbers, oh sorry, right? Okay, if these are numbers, you usually multiply them together. But now you have a differentiation. Okay, so what this means is this times this and this acting on this. So we are taking the differentiation of C with respect to Y. Okay, as another example, we just take this times this plus we're taking the differentiation of Z, sorry, A with respect to Z. Okay, so you take the differentiation of B with respect to X and then you multiply it with K. So what this means is, okay, for the first case, it'll be CY I, like that. And then the next one will be AZ j. And then the next one will be b x k. Okay, so remember, cy is a short for this. Az is a short for this. Bx is a short for this. Okay, so these subscripts are abbreviation for partial derivatives. Okay, partial derivatives. Now let's do the opposite direction. So we're gonna take this, this, this. Okay, so do a similar thing, except now we have to subtract these results away. So the first one states C X J. The next one states B Z K. And then the next one, sorry, this is I. The last one is A Y K. Okay, now group the like terms together. The I with I, CY minus BZ I. The J with the J, AZ minus CXJ. And the K with the K, BX minus AYK. Okay, so this is curl of F. This is curl of F. Now let us do the same thing for curl of G. So this time I'm gonna go through it faster because this is very similar to uh yeah, to curl of F. So this, sorry, it's supposed to be G. Okay, so this will be I, J, K, partial derivatives, and then the entries of G is D, E, F. Okay, I, J, partial derivatives, E, E. Okay, so Chris, Chris, Chris. J's. So the first one is FYI. The next one is DZJ. And then the next one is EXK. Then now we have to do the opposite direction. So minus away this, minus away this, minus away this. So the opposite direction will be FXJ. Then this one will be EZI. Then the last one will be DYK. Okay? Then after that, you group the like terms together. So this plus this, Fy minus EZI. Then j with the j plus dz minus fx j, and then finally this with this ex minus dy. Okay, so this is curl G. So next, what do we need? We need to dot product them. So remember, let's bring back this statement. So we have already found curl F and curl G. So let's substitute what we know. So G is DEF. Then we need to dot product with the curl of F. So this is from the result that we got earlier. The result that we got earlier is CY minus BZ, AZ minus CX, and BX minus AY. Okay, minus F is ABC. And then the curl of G is what we got just now, which is FY minus EX, DZ minus FX, EX minus DY. Okay, so dot product. Okay, dot product means this times this plus this times this plus this times this. Okay, so I'm gonna expand it out straight away. Okay, take care when doing the other dot product, because after you take this multiplied with this, right? Don't forget you need to expand this negative sign. Okay, so this negative sign needs to multiply to him and multiply to him. Okay, so that's why minus and plus will give you minus, whereas minus and minus here will give you plus here. Okay, so let me write this clearly. This is plus AEX. Oh, sorry, this is AEZ. Is it? Yeah, sorry, I wrote wrongly. This is EZ. Okay, yeah, this is EZ. Minus BDZ plus BFX minus CEX plus CDY. Okay, so this is the right-hand side. Okay, it's already in the simplest form. So now we compare the left-hand side and the right-hand side. So let me copy the left-hand side for our comparison. Okay, so this is the left-hand side. Let's see if the terms match. So BXF, here, it's over here. BFX, CXE is over here, minus CXE. Minus CEX, minus CEX. CXD, wait, CXD, is CXD here? Oops, they copied something wrongly. It's supposed to be CYD. Wait, let me go back up, let me go back up. That means I made a writing error here. Yeah, okay, sorry. The mistake that I made is I'm partially differentiating this and this. So this is supposed to be Y and Y. Okay, so that means this is supposed to be Y and Y. Okay, so that means down here it should be Y and Y as well. Okay, my bad. Okay, so let's continue. CYD, CYD, CDY, CDY, AYF is this one, minus AYF. AFY is AFY. EZE is over here. AZE. Okay? AEZ, AEZ. Minus BZD, minus BZD, minus BDZ, minus BDZ. Okay, so left hand side is equal to the right hand side. Yeah. Question 4. Okay, question 4 states if the velocity field of a fluid flow is given by Q equals to nabla phi, where phi is a scalar function, show that the flow is irrotational. Okay, show that the flow is irrotational. That is to say, show that the fluid particle has a zero rotational velocity. Okay, nabla cross q gives the rotational velocity of the fluid. Okay, so we know that q is this. So what we need to do is prove that nabla cross q is equal to 0 in the 0 vector. Okay, and then we are told that q is this nabla cross f. So we need to replace this with nabla phi. Sorry, nabla phi. So let's find out what is the value of this expression. So first, we need to find this, the gradient of phi. Gradient of phi means, okay, replace nabla with its definition. We have phi. So phi I need to scalar multiply into each entry. So that means phi x, phi y, phi z. So partial derivatives of phi in each direction. So now I need to take the nabla cross this. So nabla cross this. Okay, I'm going to replace this with this result that we got. So, oh, and I'm also going to replace nabla with its definition. Cross this. Okay, so we need to find the cross product of these two vectors. To do so, we need to find the determinant of this structure. Okay, so to find the determinant, we need to take the Chris. So this will be phi zy plus phi xz plus phi yx. Then they do the opposite direction. So minus away all these crosses. Minus phi zx minus phi yz minus phi xy. Okay, keep in mind, what is the notation here? For example, this, right, is short form for partial derivative y and then partial derivative, sorry, my bad. It's supposed to be z here, then y. Okay, let's take another example. This shows partial y first, followed by partial x. Okay, another example, this is partial y first, followed by partial z. Okay, okay. Here's another fact that you have to know. You have to know for a fact that this is equal to this in general. Okay, so if I swap the order of the derivatives, they're the same thing. Okay, if I do differentiation with respect to x first, followed by with respect to y, it is the same thing as differentiate with respect to y first, followed by differentiation with respect to x. Okay, so this means this is the same thing as this. So even though I swap the order of the derivatives, they still possess the same value. Okay? Having that knowledge, we can do some simplification. Okay? Since it doesn't matter if the derivatives are swapped, right? This has the same value as this, except they're opposite signs, so we can cancel them. This minus with itself. Same thing with zy and yz. Same thing with xz and zx. So you see, at the end of the day, we get the zero vector. Okay? We get the zero vector. So we've proven it. We've proven that nabla cross q is equal to the zero vector, meaning it is irrotational. Okay, so that's the definition of irrotational. So if q is said to be irrotational, its cross product with nabla must be 0. Okay, finally, let's look at equation 5. Okay, so nabla squared phi is equal to 0. Nabla squared is, okay, sorry, find the values of p such that this function will satisfy this equation at all points except 0, 0, 0. Okay, so let us first find this left hand side. So nabla squared phi, right, has a definition of this. Okay, this is just definition. It is defined to be like that. There's no why it is like that. That's the notation only. So let's go find what is this. First, let's do this one. Okay, so this is equal to, so replace it nabla with its definition. Then scalar multiply phi into each entry. So that means you are differentiating phi with respect to x, differentiating phi with respect to y, differentiating phi with respect to z. Okay, so now we need to dot product nabla with this. Okay, so replace this with the result that we got here. So equals to, and replace nabla with its definition. Dot product x, y, z. Okay, so what this means is this entry acts on this entry plus this entry acts on this entry plus this entry acts on this entry. That's the definition of dot product. Okay, so this will be xx, yy, and zz. So, for example, this entry means d squared phi dx squared. Basically, the second order partial derivative. Okay, so that's what it stands for, second order partial derivatives. So we want to satisfy this being equal to 0, right? This being equal to 0. Wait a minute, I forgot to, sorry. This is a mistake. It's not like this. Remember, dot product means first entry times first entry plus second entry times second entry plus last entry times last entry. Okay, so this must be equal to 0. That's what the question says. Okay, that's what the question says. They said this is equal to 0. Okay, so this 0 is here. Okay, so that means we need to find each of these terms first. Okay, so remember this actually means d squared phi dx squared. So they told us phi. Okay, so this means I need to differentiate that, and then, so what is d phi dx? D phi dx, right? They give us an expression. The expression is, okay, x squared plus y squared plus z squared to the power of p. So to differentiate this with respect to x, okay, treat y and z as constants. So power bring down, power minus 1 times the differentiation of the inside, which is 2x. Okay, so we need to take the second order derivative, which means we differentiate this result. So 2px x squared plus y squared plus z squared. So 2p is a constant. We can just leave that out. Okay, let me go down to the next line because this is a bit too messy. Okay, 2p is a constant. We can leave that out. You see, we have some function multiplied by another function. So we have to use product rule. Okay, we have to use product rule. Yeah, okay, so it's going to be very long. So keep differentiate. So differentiate will be, wait, let me see what I did. Yeah, okay. Power bring down power minus 1 times the differentiation of the inside. So if I differentiate this with respect to x, it will be 2x. Okay, plus now differentiate x will become 1 times differentiation of this will be like so. Okay, so to make my life simple, right? It's very long to write all this, so I will abbreviate r squared x squared plus y squared plus z squared. Okay, because it's so long to write all this, so I will short form it as r squared. Okay, so this will be 2p. Okay, so you see, I can replace this with r squared, this with r squared. So if I simplify the first term, it will become 2x squared p minus 1 r squared to the power of p minus 2 plus r squared to the power of p minus 1. Okay, what am I going to do next? What I'm going to do next is factorize. Okay, so the common factor is this and this. So what do we factorize? R squared to the power of p minus 2 or r squared to the power of p minus 1? The answer is you factorize out the smaller one. Okay, you factorize out the one with the smaller power. So which one is bigger, p minus 2 or p minus 1? It's p minus 1, right? Because it's 1 less than p, but then p minus 2 is 2 less than p, so p minus 2 is smaller. Okay? So we can factorize r squared p minus 2 out, leaving behind 2x squared p minus 1 plus. Okay, so how do I factorize this? If I factorize it, means I divide. Okay, so what is this divided by this? Okay, based on the laws of indices, this will become the same thing, but you minus away the powers. So same base, but you minus p minus 2. Okay, so what would this become? This will become p minus 1 minus p minus plus 2. So p and p can cancel, leaving behind 2 minus 1. 2 minus 1 is just 1. Okay, so what you're left with is just r squared. Okay, so that's how you factorize out that. Okay, so this is for xx. What about yy? Okay, yy, you can do the whole thing again, but I'm not going to. What I'm going to do is you just use this similar result. So this will become this, except now you change this x to y. Okay, same thing with z. You change this to z. Okay, you change this to z. Okay, so now what do we do? Remember, we say that this is equal to 0, right? And then we just found this, this, and this. So we need to substitute them. Okay, we need to add these three terms up and then equate them to 0. Okay, so let's take a look at these double derivatives. Notice that they have a common factor of this, this, and this, right? These are common factors. So if we know that these are common factors, xx plus yy plus zz equals 0. We can take it out. So the common factor is 2p r squared p minus 2. Okay, now let's check what's inside the brackets. Inside the brackets, we need to add this term with this term with this term. Look at what are the common factors between these three terms. The common factor between these three terms are 2p minus 1, 2p minus 1, 2p minus 1. So we shall factorize that out also. Okay, so 2p minus 1 is a common factor, leaving behind the terms that are different. X squared, y squared, z squared. So x squared plus y squared plus z squared. Okay, then over here, you see, r squared plus r squared plus r squared, that is 3r squared. Okay, so plus 3r squared equals to 0. Notice that x squared plus y squared plus z squared is r squared. So let's okay, so we can replace this with r squared. And then notice that inside this